Thank you all for coming to the first lecture in the IDSS Distinguished Speaker Series. This is going to take place once a month, exactly at this time, exactly in this room. And our objective from the Distinguished Series is to highlight the importance of rigorous thinking in solving societal challenges. So we try to bring examples of research and people who have been thinking deeply about problems in a very rigorous and systematic way. And then there's nothing better than kicking off the series with Professor Daron Acemoglu from economics. Daron is the Elizabeth and James Killian Professor of Economics and a core member of IDSS, and clearly a thought leader in the United States and in the world. We were just having a conversation. I could think we can have a conversation for 3 more hours. There's nobody that I know that thinks deeply and broadly and thoroughly as much as Daron does. He has made enormous contributions in the field of economics, political economy, development economics, income distribution, evolution of technology. He's also made contributions in engineering, in collaborating with faculty in areas of transportation and others. And he's also made contributions to computer science and collaborated with many social scientists. I can keep going about all the stuff that Daron has done in his career. But certainly somebody that is at ease talking to a lot of people and making impactful contributions within different fields. He has been recognized by many awards. I won't mention all of them, but I will mention a couple. One is the Clark Medal he received in 2005 for his deep and thoughtful contributions in economics, and is a very highly prestigious award. He's one of the most, the top 10 cited economists in the world. I think that's an incredible honor, but one that is actually, I like, really interesting, and that is he is one of the most favored economists in the world by a survey done among economists. I would say he's one of most favored faculty at MIT, probably one of my favorite economists at MIT, so welcome.
Thanks, Munzer, thank you. Thank you very much for that very nice introduction. It's particularly notable that Munzer mentioned my important contributions to transport systems because that was joined with him. So, thanks also to Munzer, Alberto, and Ali for inviting me. It's a great honor to be here, and I'm going to talk about fast and slow learning from reviews. It's joint work with Ali Makhdoumi, also Daglar, and Azar Akshmalekian, who is at Toronto. So I have the triple pleasure of presenting in front of my co-authors who probably know the paper, not probably, definitely know the paper much better than I do. So there's no winning here. Okay, so what is this paper about? So the increase in online trade and online social interactions have also changed how we acquire our information. If you think of how you decide whether a particular option is the right one for you in terms of which neighborhood to live in, which restaurant to go to, which product to buy, which political party to support, a lot of that information 30, 40 years ago would come from observational data from your friends and neighbors, or from communication with even a smaller group of people who were your closest friends or sources of information. Today, we have an entirely different type of informational environment in which at least some additional amount of data comes from the same online platforms that we use for interacting with others, for sharing our social experiences, and most importantly for today's talk, for making our purchases. The question is, what sort of informational aggregation properties that online platforms are going to present? We know there are a lot of concerns about internet acting as an echo chamber, not be providing the right type of information. I think these are real concerns. But one way of trying to make progress on this is, of course, by empirical work, but I think also trying to clarify some of the theoretical issues that exist in this space is an important step, and that's what we're going to try to do in this talk. But one important issue in which we're going to depart methodologically from the previous literature, and I think it's both interesting from a technical point of view, but also from a substantive point of view, is that we're going to not just worry about whether the dispersed information of thousands of users are being aggregated, but how fast, how efficiently that's going to be taking place. So in other words, we're going to be looking at the speed of learning. The reason why this is sort of methodologically interesting is because, of course, not all learning is made equal. You can have extremely slow learning versus relatively fast learning, and we might care about that. And substantively, on the online platforms, of course, we do. So to say that the reviews in the Amazon are going to aggregate information, but that's going to take 20 years is very different from the first 50 or 100 reviews are going to have a lot of information in them, so that within about a month or two of a product being out, the Amazon reviews are going to be very informative. So those two are very different, both from a social point of view and from the business model viewpoint of Amazon and other online platforms. So this is what we're going to be sort of focusing on. And in our model, we're going to have individuals who have a decision to join a platform, an online platform. Once they join, they're going to see reviews or some summary statistic of the reviews that are left by others who have previously purchased the same item. And on the basis of that and their own realized types, such as preferences, they're going to make a decision to purchase the good. And once they purchase the good, they can decide to leave a review about their enjoyment from the good. So the movie you watch, was it a 5-star, 4-star, 3-star, or you just cannot be bothered to leave any information. So that's the sort of setup that we're going to be looking at. So what's the main issue here? So this is, at some level, a version of an observational learning model, meaning that what you are doing is you're getting signals from other agents in the model. Those signals are related to their actions, so it's not a communication model. And from those signals, you're going to be trying to make inferences about some underlying state of nature. So one class of models of this sort are the canonical social learning or observational learning models in economics, which are often associated with the sort of herding phenomena. And here, we're going to be dealing with a sort of a different beast from a substantive economic point of view. The main difference is that in the herding social learning models, the signals you receive are themselves functions of the belief of the individuals who are acting before you. So in particular, you see people's actions. But the actions that they take, for example, whether they decide to buy the good or not, is going to be very heavily influenced about the information that they themselves received from the past. So that sort of information confluence is going to put severe limits on how quickly and how efficiently information can get aggregated, and herding, where everybody follows some moderate but far from perfect bit of information, is sort of an extreme case of that. Now, when it comes to reviews, the issues are different. So the strictest form of herding is less likely to happen when you're thinking about reviews. Why? Because conditional on buying and enjoying the good, the information that had actually pushed me into buying it is not so relevant, because I've actually sort of observed the quality of the good myself. Of course, reality is more complicated. I may be so weak-willed that the fact that some people had told me this is a great product might make me think that it's a great product even though it sucks. But leaving that sort of pathological outcome aside, reviews are going to be directly a function of my own enjoyment of the good. So that's going to solve, to some degree, the herding issue that I was buying the good, and people saw me buying on the basis of the information that I obtained from others, and therefore, my own information is being swamped by what I learned from the previous experiences already. But instead, we're going to be grappling with another issue, which is what we're going to call a selection problem or a selection issue. What is a selection issue? Let me try to illustrate it with this slide. So here on the left, you have a book by Naomi Klein on capitalism and climate. On the right, you have a book by, well, my pupils are dilated, so I can't quite see it, so I don't know what the guy's name is, some Tim Bell or some such thing. And what you'll see is that on Amazon, they both have quite a few reviews, so it's not like one weird guy. And they both have over 4.5 in terms of their score. Now, if you know Naomi Klein, you'll be hard-pressed to find that 4.5 out of 5 randomly chosen people could like her book, because if that were the case, we would have the Communist Party in power in the United States. But on the right-hand side, that's a book that claims that climate science is entirely a hoax, there is no global warming, and all of this is a sort of made up thing in order to reduce America's economic vitality. So, if this was just some same people, it is absolutely impossible for both of these books to get 4.5 stars. What's going on is that, of course, only a certain type of people buy Naomi Klein's book. They tend to have a political view similar to hers. They start with a sort of tastes very aligned with the message of her book, and of course at the end they like it. And the people who buy Tim Bell's book, on the other hand, already start with the view that climate science and all these left-wing East Coast elites are terrible, and they tend to like that book. But in the extreme, this selection problem, as in this case, would make it very difficult for us to learn because it's just the echo chamber that I mentioned at the beginning. So the question is, what are the conditions and how this selection problem can be overcome despite these natural tendencies that people are going to make purchases and then rating decisions on the basis of their tastes? So against this background, here is what we do. We're going to look at 2 complementary models. Essentially, they're the same model with two different informational assumptions. The first one is sort of like a warm-up exercise, because it's not very realistic, but I think it clarifies a lot of the issues, and it's easier. It assumes, just like the early part of the literature on social learning herding models, that you observe the entire history of all the reviews. Not only that whether Ali and Alberto and Munzer left 3 stars, 2 stars, but in what sequence and so on and so forth. But from basic intuition, you can see that in that case, we're going to have that optimal beliefs, Bayesian beliefs, the beliefs correctly calculated, are going to follow a martingale, so we can use martingale convergence theorem and related methods in order to analyze this case. The more realistic case, which is the sort of the more important contribution in some sense, is the more realistic one where, just like as in this example, you don't see the sequence and the exact things, but you see a summary statistic of the reviews left. For example, 4.5 stars. Or you might see, as I'll show you in another slide, in fact, I'll show it to you now, you might see, for example, not 4.5 stars, but the exact distribution of 5 stars, 4 stars, 3 stars, et cetera, et cetera. But this is still a summary statistics. It's not going to have the martingale properties. And in both cases, what we're going to show is that under some mild, reasonable, but still important to note assumptions, we're going to get asymptotic learning. And in both cases, actually, asymptotic learning is going to be exponentially fast, though the rate at which it happens itself is interesting and varies quite a bit depending on the structure of the information and the distribution of preferences and distribution of heterogeneity that exists in this setup. And these results are going to enable us to then go forward and ask questions about the design of these online platforms. What are the features of online platforms, or the way that they communicate information that might make it better or worse in terms of the speed of learning? And so, for instance, going back to here, is it better for Amazon from the viewpoint of speed of learning to provide a summary statistic like this, or give the exact distribution of 5-star, 4 stars? Or is it better for Yelp to give just a summary or the evolution of the average rating over time? So those are the sorts of questions that we may be able to answer. Now, there's a large related literature here. I'm not going to go over it in any great detail. Suffice it to say that some people in this room have contributed to it, but I was contrasting it to this literature here, which is the observational learning models, or this one here, which sort of generalizes that away from martingale type settings to general network settings. But the key issue, as I've sort of indicated, is going to be moving away from the key aspect of herding in the existing observational learning literature, but to the selection effect, and then turning the focus on the speed of learning as well as whether there is learning or not. Any questions at this point? All right, let me jump into the model. Here is the model. I'm going to focus on a single product. And there is a sequence of potential customers who are going to first decide whether to join the platform. And then once they've joined the platform, they're going to see the reviews or some summary statistics of the reviews left before them. And then at that point, they're going to make their purchase decisions. So a couple of things about these customers. First of all, we're going to assume that there is some costs of joining the platform. So there is a non-trivial decision for these guys to actually join the system. And then this, at the time where they join, we're not going to let them to condition that decision on whether they are the first, second, third, or fourth customer. So it's just a relatively simple problem. Once they enter, now they're going to see the relevant information given the setting we have specified. So in particular, as I've highlighted, they might see the full history, which is the entire sequence of actions before them. So if I'm Mr. T, then I can see A1 to AT minus 1, or they can see a vector of summary statistics like the distribution of 1-star, 2-star, etc. And we're going to refer to these two cases as full history and summary statistic. More specifically, conditional on entering, here is the utility function that individuals are going to have. My utility is going to have a couple of terms in it. The first one is theta t, then zeta t, then q, and minus p. Theta t is my type. So this is something I know before, whether, say, for example, I think that climate science is a hoax, or the market system is doomed to fry the planet. So that's going to be measured by theta t. I know that before I make my entry decision, so I have some idea about how much I'm likely to like this particular product. Once I enter, then two more things are going to become relevant. One is zeta t. That's going to be, once I enter and I purchase, that's going to be the that's going to be my ex post enjoyment from the good. So I might like I might like books that are pro-climate science, but I read this book and I see the style doesn't mesh with me, or she uses arguments that I think are vacuous, etc. So I may not like it. That's going to be captured by ZT. Plus Q, which is either 0 or 1, that's the true the state of the world. So Q equals to 0 means this was actually a low quality product. Q equals to 1 is a high quality product. And that's what I'm going to try to learn. And P is the price which I face for purchasing this good. Now, what is the information that I have when before I actually make my purchase decision? Well, I know theta t already, and I know price. Zeta t, as I mentioned, I will only experience after purchasing the good. So the only thing that's relevant for learning here is Q. And Q is actually the thing that's common between me and the previous customers, because everybody's preference depends on Q here. And so what I can do is I can look at the reviews left by previous customers, and I can try to form some beliefs about Q. So that's the problem. I observe the set of reviews, and out of that, I'm going to form my beliefs. Given theta t and price, which I know, I'm going to make my purchase decision. B equals to 0, not buy. B equals to 1, buy. Okay. What happens after I purchased a good? After I purchased a good, I experience my utility. And I'm going to, at that point, assume that I decide whether to leave a review or not. And the review decision is not going to be strategic. In other words, I'm not going to try to fool anybody. I'm not going to try to sort of strategically communicate something other than the quality. But I'm going to truthfully react to the enjoyment or lack of enjoyment from the good myself. Now, this is why we have motivated this model with product decisions. If this was a political model, online communication, online learning is super important for political things, but there, sort of truthful or quasi-truthful reporting may not make sense. I might not believe something, but I might still try to convince other people. After all, that's what politicians do all the time. So that's sort of absent here. So in particular, we're going to assume that there are a bunch of thresholds. These are given by the lambdas here. And if my enjoyment is below the lowest threshold, I'm going to leave the most negative review. And then there's going to exist some other thresholds between which I'm indifferent. I'm not going to leave a review. And if it's above, then I'm going to leave one of the positive reviews. And then we rank the reviews from minus K1 to K2, 0 corresponding to no review. And depending on the information structure, you may assume whether no reviews are observed or are not observed. So the platform might give you the fraction of people who have left the review out of the customers who've bought online, or it may just give you, just like Amazon does, only 1 star, 2 star among those who have left reviews. Okay? Those are all decisions for the customers. Okay. So the key thing, therefore, is going to be here is going to be this sort of thresholds, lambdas, which I'm going to take as given for now, and I'll talk about how those can be manipulated or changed. So one thing that I should note is that for the analysis, I'm going to assume these thresholds, lambdas, are the same for everybody and are therefore known. That's, of course, not a very realistic assumption. I could have an idea that if Sanjoy leaves a negative review, he didn't like it, but how much did he not like it? Well, that doesn't really matter. So you can add an idiosyncratic error term to the thresholds. And you can see that if you did that, as long as that's IID, that would just act like the zeta, so none of the analysis would change. So that's really without much loss of generality, except that instead of working with the distribution for zeta, you would have to work with the distribution of zeta plus the error terms that affect the threshold. Okay? So now the next assumption seems sort of innocent, but it's actually a very important assumption. So we make a richness assumption, which says that these zeta ex post enjoyment term is got sufficiently wide support such that regardless of what your theta is and what the quality is, all sorts of reviews are possible. So an alternative might be that this zeta is very concentrated, so the most positive review could come only if the good is good, and I am one of the fans of the good. So we're not going to make that, and that's going to be very important, of course, for inverting the signal for trying to draw inferences. So I'll come back to the role of that assumption in a second. Okay? All right. So before we go forward to our real analysis, let me just note one little result, which sort of is sort of independent from the rest of the analysis, but it sort of gives it some context. You can see that in this setting, if the platform wants to maximize the number of people who join the platform, for example, because it's generating some ad revenue or some such thing, then the platform itself would have an incentive to choose a rating system that provides the fastest speed of learning. So in some sense, later on, we're going to come and we're going to talk about, now that we've done the analysis, let's use this analysis for saying, is this the review system better than this one? Is it better to give more information to people? Not always, but sometimes yes. So all of these questions are also relevant from the viewpoint of the platform. Why? Well, because when people enter, they're making an economic decision. They want to get utility. And if they're not learning much, there's very high probability or relatively high probability of making type 1 and type 2 error. Buy when the good is not good for you, not buy when the good is good for you. So the faster is learning, the smaller are the probabilities of these type 1 and type 2 errors. And therefore, we have more incentive to join because we're getting a better service from the online platform. So therefore, the online platform's incentives are aligned with the choice of a faster learning system. OK, now with that out of the way, let's come to the heart of the problem. So as I said, we're going to analyze this under two cases: full history, where we have all of the observations, all of the actions from the past being observed, and then the summary statistics. So let's start with the full history. And the key thing here is that we can proceed by defining a public belief. Remember, the review system is useful for me insofar as I am acquiring information about the underlying state. This is capital Q. So let me summarize that information, since Q is binary, with little qt, which is the probability, given this whole information sequence that I have received, the probability that the big Q is equal to 1. So that's the given there. And we refer to that as public belief because it's built only conditional on public information. Anybody who was in your shoes could form those beliefs as long as they know how to compute Bayesian updating formulas. Okay. So then, on the basis of this, I'm going to make my purchase decision. What is my purchase decision going to be? Well, I have a linear utility. I know my theta. I know the expected value of zeta, what's the enjoyment I'm going to get once I enter. And I have now just to obtain the expected value of Q, which is the underlying state of the world. As long as these three terms are greater than price, or these three terms minus price is greater than 0, I want to buy. Otherwise, I'm not going to buy. And then once I enter, I leave a review. End of story. OK. All right. All right. So how do we do the analysis here? As I've already sort of highlighted, the public, in this case where we observe the full history, we're going to have that the relevant object, the public belief in this case, is going to follow a martingale. So in particular, instead of working with Qt, I will alternately work with Qt or its likelihood ratio, so the little lt, which is Qt divided by 1 minus Qt. Okay? So lt itself, updated by Bayes' rule, follows this equation here. What does that say? Well, lt plus 1 tomorrow is equal to lt today plus the likelihood ratio of the action that actually got realized. So what am I trying to do? I'm trying to find out whether the underlying state is Q equals to 0 or Q equals to 1. Now, I can do this sort of the hard way. I can take all of the signals that have been realized so far, and I can apply the Bayes rule. But I can do this sequentially also. Imagine that somebody before me has already computed the likelihood ratio. That's LT. I can just start from that likelihood ratio that already has optimally all of the information up to that time. Plus, I get one more piece of information, which is the action today. And I ask the question, what's the likelihood of this action having come when the underlying state is Q1, divided by the likelihood of the same action having been realized when the underlying state is 0. So that's this object here. It's conditional on A, or it's given the probability of the A being realized, and Q equals to 1 versus Q equals to 0 in the numerator versus denominator. But there's also one other important thing which you should note because it's going to play an important role. All of this is conditional on little qt. Why is this conditional on little qt? Well, that's because of the selection effect. So I don't know who the previous person who generated this review is. I have to form beliefs about whether that person himself was a high theta, low theta, medium theta person. But that depends on qt, because qt, which is, or LT, last period's information, is going to determine who enters the system. And who enters the system is going to be relevant for my expectation about theta, and that theta, of course, is going to be relevant for what sort of signal I should expect. In the extreme case, if little qt is such that only the diehard fans of denying climate science are going to enter, I should be a little bit skeptical about reviews that says this book that denies climate science is great. So that's all in that probability coming from the conditioning on the little qt. OK, so that was for a given realization of A. So now this thing here gives us the governing stochastic process for the likelihood ratio. Again, LT plus 1 is equal to LT, but then its law of motion, or a stochastic law of motion, is going to be given by the probability that the different A's get realized under the true state of nature. So I, as the user, of course, don't know the true state of nature, but when you, as a modeler, you want to think about how my beliefs evolve, you want to generate the little A's under the true state of nature, because that's what generates the relevant information. So that's why here we have Q star, because we are conditioning the realization of these actions on the true state of nature. And then those are these things which I explained earlier on, which are the likelihood that my ex post enjoyment falls between these different thresholds. All right. And then one more piece of, one definition here. And then after that, I can present the main result for the martingale convergence case. So this is, of course, bringing coals to Newcastle. I shouldn't be defining KL divergence here. All of you guys have been steeped inside that for years, but here it is. This is the definition of KL divergence. And some of you may have already guessed that once I've talked about exponential speed of convergence, this was going to be somewhat linked in one way or another to KL divergence, and in fact it's going to be, and that's where this theorem comes in. Okay, so it says that as long as this condition here, so let me focus on the second part of this theorem. This is the sort of the more interesting part. So as long as this condition here holds, and I'll interpret that condition in a second, learning will occur, and moreover, it will be exponentially fast, and the rate of convergence is given by this expression here, by this KL divergence between two probability distribution. One of them is the probability distribution of generating the reviews when the underlying state is 0 and the public belief is 0. And this one is when the underlying state is 1 and the public belief is 0. Okay? So now let me first give you 2 bits of intuition about this, and then I'll sort of go over the key parts of the proof just to fix a few ideas, and then we'll move on to the more novel part, which is the summary statistic. So the first thing I want to do is I want to highlight why it is that this condition here is necessary. So let's look at the blue condition. What does the blue condition say? It says that the price is sufficiently high that even if I subtract from the price the maximum value of theta, so the maximum, the highest type in terms of liking this product, plus the expected value of zeta, which is the same for everybody, then it's positive. Well, if that's the case, it means that if I believe the product has quality 0, nobody will enter, because the price is too high. Even if I have the best taste for this product, I still won't enter. But if that's the case, there will be some sample paths with positive probability that will get me to a low enough assessment of the quality that entry will stop entirely. But if entry stops, then learning will stop. So this is the case in which learning will not happen with positive probability. So the red condition is the converse of that. As long as that inequality is the other way around, there's no way to stop the learning. Even if we become extremely pessimistic about the quality of the product, there are some diehards like people who like books like this, or who like mixers that are green and blue mixed. They're going to purchase the good. As long as they purchase the good, information will trickle in, maybe slow, maybe fast, but it will trickle in. If it trickles in, learning won't stop. That's the first part of the intuition. The second part of the intuition, which is about why learning is exponentially fast and is related to KL divergence. Well, the exponentially fast, let me sort of give a very loose intuition, which is, once the reviews get going, they're actually fairly informative if you can invert the selection problem. And here we can invert the selection problem because of the richness assumption, because the richness assumption is going to guarantee that we know different signals are going to occur for the different underlying states of nature, and that's going to enable us to learn in a way that I'm going to explain in a second. And the reason why KL divergence comes, because asymptotically this turns into a binary hypothesis testing problem. What I'm trying to find out, just like in a hypothesis testing problem, is that whether the data that I observe is generated from a probability distribution that conditions on Q equals to 1 or Q equals to 0. So that's why the KL divergence comes in. All right, so what's the proof? So here is the proof. And this part is actually pretty straightforward. It just uses the martingale convergence theorem plus the fact that under the richness, and that's why, again, I'm emphasizing the richness assumption, which is sort of enabling us to overcome the selection problems, we can get enough of information. So in particular, we know that, so we're focusing on the case in which that this red thing here is negative, so we're not going to get stuck by not buying this product. And we also know, here is the argument, but it's pretty straightforward, that the likelihood ratio is a martingale. But the key observation is here. The probability that this thing here is z, by the way, I should have highlighted that. This ratio of probabilities we've called z. So this ratio of probabilities being greater than 1 plus delta is always positive. Why is that? Well, because since there is the richness assumption, there is always the likelihood of getting every signal. But think of the most positive signal, the 7 star or 8 star, whatever is the most positive signal. Well, that's always more likely when you have Q equals to 1 than Q equals to 0. So therefore, when you get the most positive signal, you should at least a little bit of updating of the likelihood ratio. So that's this thing here. This probability that this is greater than some positive delta is at least eta. But then we can write this probability distance between the likelihood ratio at t plus 1 and t as greater than epsilon delta as the probability that LT is greater than epsilon and this z minus 1 is greater than delta, or conditioning on LT, that's really nothing other than this eta here and the probability that LT itself is greater than epsilon. But since the martingale convergence theorem, LT plus 1 converges to LT, there's nowhere for this object to go but to 0, so therefore we cannot be converging to the wrong thing. So therefore, the proof is very simple. The martingale convergence theorem tells us that almost surely we converge somewhere, and we just have to show that given the richness assumption, which is that the informative signals continue, we cannot converge to the wrong place. The sort of newer part, at least for me, was the speed of learning. So that is, I'll again won't give you the details, but just the broad outlines. How much do I have? 15 minutes. Okay. So let me do this extremely quickly because I want to get to the more substantive stuff. Well, not the more sort of design sort of questions at the end. But I can write LT successively substituting for the likelihood ratio as the initial likelihood ratio and these ZT terms, the probability of the actions that are realized under Q equals to 1 divided by Q equals to 0. Then take logs divided by 1 over t, and that's the log of the likelihood ratio, and that's given by a term like this. This is exactly what the form of this term looks like the KL divergence. Now, the complication here is that these are not independent terms as opposed to the simplest form of binary hypothesis testing where you have IID, conditionally IID samples. But what we can do is you can sort of show first exponentially fast convergence, and then once you have converged, the dependence gets sufficiently small that you can find bounding functions, and then you can do the convergence using these bounding functions. So that's the general proof. Now, let me mention one other little result in the martingale case, because it's going to have parallels in the sort of summary statistic case. And that is that even if we are not in the case where we don't observe everything that has happened in the past, as long as we observe a subsequence, and that subsequence itself is constructed in a way that's not informative. For example, the subsequence is not conditional on the true value of Q. If the subsequence of people who have purchased a good, and when you purchase, you don't know the true value of the Q, then you can again apply a sort of a martingale convergence type reasoning, and more or less the same argument goes through. So in other words, in general, and we're going to see the same trick when we come to the summary statistic, we don't need that the relevant thing that we observe is a function of time. It could be a subsequence of time. We might see things that are realized at some random points in time. We can go back from there to the information that we want. All right, so now we come to the summary statistics. And as I explained at the beginning, instead of now observing the full history, we're going to observe some vector of 5 stars, 3 stars, 2 stars, etc. In fact, what I'm going to do is I'm going to simplify things. And during the presentation, I'm going to talk about the simplest case of a summary statistic. Imagine we have a rating system in which you can either leave a positive check or nothing. And what we tell you is the number of people who have left checks among those who have bought. Okay? This is just one of the examples we can talk about, but it has the advantage that it's one-dimensional, so I can lighten up the notation a little bit. Okay? So in terms of notation, we're going to be using the notation that ST here is the summary, some average, so 1 over tau. So we've observed tau reviews, for example, or tau purchases, and this is the number of people who have left 5 stars or the check mark among those. Okay? Now, the key thing here is that we can again write a relatively simple stochastic process for the evolution of these summary statistics. And it's written in the vector notation. And what is ST plus 1? Well, ST plus 1 is linked very strongly to ST. ST is, the fraction of, say, likes yesterday. And how does that evolve? Well, the way it's going to evolve is that today there's somebody else who either likes it or not likes it. So what is today's average? It's the same as yesterday multiplied by tau over 1 plus tau, plus either you get 1 or 0. So if you get 0, then the average goes down a little bit by 1 over tau, or 1 over tau plus 1. If you like it, it goes up a little bit. Okay? So that's this thing. And of course, it's not a martingale because I don't have the information that the previous person had. All I see is this average. Okay? So now it is harder to overcome the selection problem. It was quite relevant in the martingale case that I could see the exact sequence. So for instance, I saw 0, 0, 0, 0, 0, 0 stars, and then somebody comes in and leaves 5 stars. Well, I can say, well, that person was probably a diehard fan of this book. But now, all I see is an average. I don't know whether it was somebody liked it, somebody disliked it, somebody liked it, or somebody, despite the fact that the book had such bad reviews, bought it and loved it, so it was the cousin of the author or something like that. Okay? So that confounding is going to make it harder for me. So we're going to introduce this separation assumption, or first as a definition, then as an assumption, which says that the distributions are separated if the probability of like when the beliefs are little q and the underlying state is q equals to 1 versus the probability of like when the belief is little q and the underlying state is q equals to 0, when these two distributions are separated in terms of their support. So for example, in the extreme case, imagine that whenever q is equal to 1, I always get everybody leaving 5 reviews. When q is equal to 0, I always get everybody leaving 1 star. Well, the only way you're going to get identification here if these two fractions are not the same, well, in this example, they're not the same. Now, in general, of course, it's not going to be a Dirac function. There's going to be some distribution. So we need these distributions not to be the same or not to be overlapping. So that's what this separation assumption is. All right. OK. So here is the result. It says that now, in addition to the richness assumption that I already imposed in the martingale case, if we also have this separation assumption so that the reviews are sufficiently informative to overcome the selection problem, then we are going to have learning, and this learning is going to be again exponentially fast, and its rate is going to be given by this KL divergence. But crucially, the KL divergence is different. And the difference is highlighted on the slide. It's the red terms. When we had the martingale case, what we were trying to distinguish were two probability distributions. One, of course, conditions on the true state being 1. The other one conditions on the trace state being 0. But what do they condition in terms of the little q, the public belief? Well, in the martingale case, I not only observe the current belief, which is the information that I'm conditioning on, I'm also observing what the public belief was yesterday. So I can really tease out what the value of the information that comes at the margin. So that means I'm essentially conditioning on both the public belief and all of the information that comes from the probability distribution. So for that reason, in the martingale case, the comparison is always, we are almost converged already to the true state, which is q equals to 0. And so at some point, I should have said this, and I didn't. I'm sorry. Of course, this was important. I'm going to do all of the statements assuming that the true state is q equals to 0 just for simplicity. And that's why it's the 0 that's relevant here, of course. That was rather important to have said, but given that my pupils are dilated, I don't see exactly what's on the slide, so I'm going by memory, and that's one part I forgot. But so the true state is q equals to 0. So what I'm trying to distinguish in the martingale case is that the q equals to 0 state, when I also, and everybody before me believes that little q is equal to 0, from everybody, in fact, does believe that q equals to 0, but the true state is q equal to 1. And if I can make that distinction quite fast, I'm going to learn very fast. Whereas in the case in which I observe a public belief, I don't know what the information that the person before me had. So all I can say is that, well, if I am learning, they're also learning. So whatever my q is, their q must be. So therefore, the distinction is between little q equals to 0 and big Q equals to 0, and both little q and big Q is equal to 1 in this case. So as a result, the rates of learning are going to be different. Okay? All right. Let me now quickly say 2 words about the proof here, because it's sort of cool, and then I'll move on to the sort of comparison of different information. So as I said, here, this is not going to be by sort of martingale arguments, but what we can do is we can try to show that when we have this property that the distributions are separated, we can exponentially fast get the fractions in the right order and then do the learning on the basis of that. So, and let me try to sort of give the intuition for that. Essentially, what we are doing is we are observing some summary statistic. So let me look at the probability distribution of that summary statistic. So that's all these L objects. So L0 is the probability of certain number of likes, I likes, when the underlying state is q equals to 0, and L1 of I is the probability of I likes when the underlying state is q equals to 1. And again, just like the likelihood ratio that has a simple recursive structure, you can get to I likes by starting with I likes, but somebody didn't like it, or you started with I minus likes and somebody liked it. So it has a sort of a Bernoulli structure. Okay? And then I can just track the distribution of these L's. And what I know is that these L's, of course, are going to be fairly complex things that are going to be overlapping, especially in small samples. So here I've drawn it in for something when there are only 10 reviews. But then under this separationness assumption, as you add more and more reviews, these L's are getting further and further apart. And then for tau, the number of reviews large enough, you can find a binomial that majorizes one of them and another binomial that's is majorized by the other one. And then you can use those binomials to actually show the convergence. And that's essentially sort of the idea of the proof, and then you fill in the details. Okay? So here, again, there is that idea. So here is the L for 30 reviews. Here is the binomial that's given by the maximal probability of likes. And sorry, yes, likes. And here is the binomial for the minimal probability of likes when the true state is 1. And then they are themselves getting more separated. And then when I get a particular fraction of likes here in this region, I know that I'm very likely to come from the blue one, and the underlying state is likely to be q equals to 0. And as I increase tau, the likelihood of ending up here is very small, so I'm getting to in the right portion. Okay? All right. So now, with the last 5 minutes, let me get to the question of design of the rating system. And there are, in particular, 4 things that I want to say here. The first one is a question that I sort of hinted at in the introduction. Is more information always good? And the answer is no. And well, there are several ways of seeing this, but let me try to illustrate this by showing that even though the full martingale case gives you more information, sometimes learning could be faster under summary statistics. Why is that? Well, here it is. Here are fix all of the fundamentals of the problem, the distribution of theta, the distribution of zeta, price. But assume that there are 3 systems here. One is the martingale. You observe everything, all the reviews. The second one is you observe a summary statistic that corresponds among all of those people who have liked among those who have purchased it. And the second one, the fraction of likes among all customers. Now, how do we rank the speed of learning of these 3 systems? So here is the answer to that. What we need to know, again, is this captured in that KL divergence. Which KL divergence is greater when we condition on the little q being equal to 0 or little q being equal to 1? And the key problem is related to the selection. Let's first do the comparison of the full history, the martingale case, to the fraction of likes among buys. So the comparison is really those probabilities. In particular, for the full history, the KL divergence is a function of the positive review when little q is equal to 1 and little q is equal to 0, only differs on the big Q. For the summary statistic, it's a comparison of big Q is equal to 1 and the little q equals to 1. So how do we rank these 2 things? Well, they're ranked as the figure shows because of the selection problem. When little q is low, only the people who are diehard fans of the product buy it. But those people are very likely to like it. So therefore, getting positive from reviews from them is not very informative. So therefore, I'm not going to be able to distinguish the true state being q equals to 1 from one in which the true state is equal to q is equal to 0, but everybody thinks it's q equals to 0 and don't buy it. Okay? So therefore, that summary, because of the selection problem, is a smaller distance than the full history. Yes, please?
So that's basically your confirmation bias discriminator.
you can call it that. But in some sense, when people talk of confirmation bias, that normally is like a behavioral story, which I think makes a lot of sense. So here is sort of a Bayesian confirmation bias. But now, imagine that instead of having the fraction of likes among all buys, we have the fraction of likes among all customers. Now the selection effect works in the opposite direction. Why? Because when little q is equal to 1, when people actually believe the little q equals to 1 until the alternative hypothesis, they're going to be buying more. If they buy more positive reviews are more likely, because anybody who buys is going to leave a positive review with some probability. So therefore now the distance between the two hypotheses is bigger under the summary, so you're going to get faster learning under the summary statistics. So by compressing the information, we have changed the way that people make their inferences in a way that makes it easier for them to distinguish the two states that they're trying to distinguish. And this sort of general lesson, though perhaps this looks particularly paradoxical, is true everywhere. So whenever we think of how fine the information is, we have to take into account how that's going to affect the inference. So here is the second result, which is going to be both substantively interesting, hopefully, and confirm that sort of intuition. So we ask the question, is it better to have a more refined rating system? So for example, one web page might ask you thumbs up or thumbs down, or they can ask you to have which one do you like? Which one do you give? 1 star, 2 star, 3 stars, 4 stars, 5 stars. So having 5 options relative to just 2 options is more refined. So does that additional refinement improve the speed of learning? And the answer is yes or no. So here is the way I would formulate it. So if we create a more refined, strictly more refined system, meaning that we somehow convince people that all of those who were previously giving thumbs up, now you're going to give 1 of 4 or 5, and that's going to be a strict refinement of the first system. Then you can show that the speed of learning always increases. But of course, there's no guarantee for that. It might well be that Dennis John was previously leaving thumbs up, and now I give him 4 and 5 stars, and he puts his threshold somewhere between 4 and 5. So he was previously giving thumbs up, and now he's going to give 3 stars. And then somebody else who was giving thumbs up is going to give 4 stars, and it's no longer a sort of a nested sort of comparison. Then there is no guarantee that the speed of learning is going to go up. So in other words, by making the rating system more refined, we can get people to cut their information in such a way that the aggregation of information becomes harder. So the details of the review system, and here, of course, our hands are a little bit tied because we've taken these thresholds somewhat exogenously, but exactly how those thresholds are going to get formed, depending on the product, depending on the rating system, depending on people's expectations, are going to matter quite a bit. And then the final thing that I want to sort of show, which sort of highlights the same sort of point, but comes back to the title of the talk, which is fast versus slow learning, is I'm going to sort of construct an example which illustrates why the place of these exact thresholds matters, and also why in the same environment you can get very, very fast learning or very, very slow learning. So here is an example where we're going to start with only 2 outcomes, dislike and like, and then, oh, sorry, this is not the one. All right, where is that? Okay, oh, it's not the right slide. Okay, let me say it in words, because I think this is not the right slide. So we're going to go from a system that had dislike, like, to one that has dislike, and love. So we add one more signal that's like a very positive signal. And then since time is short, let me not go through that, but we're going to construct a particularly simple example, perhaps a little bit extreme. So this is the distribution of zeta. So people have a bimodal ex post utility conditional on experiencing the good. They are very likely to, they may hate it or they may love it. And then there's some little bit of mass here. And then we sort of work out the thing. So this is what you're going to get, for instance, if you have the probability of like. So this is the area of probability of like under q equals to 1, probability of like q equals to 0. But a lot of the mass is on these thick lines. So that means that these two probabilities are very similar. So the distance is very small. So you're going to get very, 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 very slow learning, almost no learning. So the probability is getting to 0. As I make this line is thicker and thicker, that probability is, the speed is going to 0. But now imagine I introduce another option. I love the product. By making the love, I might shift this here to here, that for you to love it, you really need to have a very extreme zeta when q is equal to 0. So I have the mass function has escaped out of this area. Now the gap between these two probabilities is huge. But if that probability, the mass being huge, means that learning is going to be happening extremely fast. So by playing with the details of the rating system, you can hit the information just with the right threshold so that you can get very slow versus very fast learning. All right, so there's one more result about the features of the rating system, but since time is short, let me skip that and take some questions.
Can you please explain what other models people may use for putting reviews, and then the effects? For example, people may look at the aggregate review when they're deciding the review, and if their enjoyment is much more than the aggregate review, they will be influenced to put a higher review than the true experience or something like that.
Right, that's a great question. So, and that gets to the heart of it. And in fact, I try to sort of talk about this a little bit in the introduction. Oh, okay, sorry. So the question, so far as I understand it, is that what happens if the existing reviews are relevant in what review I leave. For example, if I see I have the same enjoyment of the product and I see other people have left a review of 3, I say, well, perhaps I also going to join them. But if other people had left 5, I also say, well, they know something, and perhaps my enjoyment was greater than I felt, and I leave 5. Or an alternative could be I react to them in the opposite way. I could say, well, they like this good. I don't like it so much. I'm going to give it a star of 1. So I could be contrarian. So both of these cases would make us somewhat closer to the herding model. Because remember, in the herding model, the issue was that the signals that I sent, or the actions of mine that other people observed, were themselves functions of the information that I got from other people. Whereas in our setting, they are only indirectly functions because of the selection effect. The selection effect determines who I am, and then conditional on who I am, my signals are only a function of the true Q. So the little q disappears conditional on my type. So in your case, the little q, the public belief, would no longer disappear conditional on my type, because little q is the same as the existing reviews. And then that would introduce a type of herding into this framework also. And I think that's... Even if that dependence is very, very small, but if it's very, very small, then we might be able to bound it. But that's not, we haven't done that here.
It can be as unrobust that way. The model that herding the curve is small, the impact of the review is having a small impact.
I don't know. That's a good question. We should think about that.
How would you adjust the model to incorporate adversarial reviews, or if I'm selling a product, I buy a bunch of fake reviews? Yeah.
That's a great question too. So we haven't done that. And my guess is that in the martingale case, we can overcome the adversarial reviews. So as long as the adversarial reviews are small, in the martingale case, you know that they're going to, as long as, if you have the wrong model of the world, you think adversarial reviews are not possible and they come, then you're screwed. But as long as you understand that there is some probability that some people are going to try to mislead you, in the martingale case, you should be okay because you see everybody has converged to 0, 0, 0. Suddenly, some couple of people come and we love the good. Well, you can say, well, this is now conditional on the sample path I have observed. That's very likely to be those guys who are trying to sell their own goods. But in the summary statistics, that's much harder because I don't know the sequence. So I don't know whether that will really throw cold water onto the whole convergence. So essentially, in the summary statistics, in some sense, I didn't say that, but I should say it now. Conditional on getting learning, the rate of learning is very straightforward, and it's pretty fast. The challenge is to make sure that even though you have this low-dimensional information, you actually get learning. And your question gets to the heart of making that more challenging in the summary statistic case. Yes, please?
So I have two questions. First question is related to, so given that judging the quality of a book is a subjective decision, how would you argue that there exists a true state to begin with? And second question is, imagine 3 scenarios where a person is deciding whether to buy cigarettes because cigarettes cause cancer, other is deciding to vote Donald Trump or not, and the third is whether to buy a high cholesterol product or not. In 2 of the 3 cases, the true state is known, whether that product is good or not.
Right.
But in case of like high cholesterol product, it is not even known whether that product is going to harm your body. So how would you, where would this model be most appropriately used?
Right, so absolutely that the relevant sort of set of questions here is that there is an underlying state that's unknown and that we're trying to learn. So, getting reviews from, religious people about whether they love their church or whatever, that's not going to be very informative. But as long as there is something to be learned, meaning that there is something that at least some significant fraction of the population is uncertain about, that's the sort of the setting for which this model is applicable. But in that case, it is still important that these experiences are subjective, even though there is an underlying state of the world, and that's what we're trying to capture with this theta and zeta. So the theta and zeta, albeit in an additive form, are capturing 2 important dimensions of that subjectivity. One is ex-ante subjectivity. There are some people who are going to like this product, who are favorably biased towards this product, and they know when they purchase it that they're going to like the product. And the second is the subjectivity of the actual experience of consuming it, or consuming that product, or consuming that piece of information, that online service, etc. And then after you do that, that subjective preference is revealed. Now, we've made that additive. We haven't investigated what happens when it's not additive, but I don't think that matters a whole lot. So that, of course, nothing in reality was going to be additive, but additive makes a lot of these mathematical manipulations easier. But as long as there is enough of that subjective thing, and then we can invert that, all of the arguments should go through.
I have a question. So what do you think the learning curve change if you have like the return option? Say
If we have, sorry?
The return option, like for Amazon you have 3 returns. So even if you don't really like it.
That's a very good question also. I think at least in the simplest way that I can answer that question, as long as I have the thresholds, or I have some estimates of the thresholds as a user, the learning framework here and the results apply. I think what the return option is relevant is for those thresholds. So as I said, we took those thresholds as exogenous. It's of course important to endogenize them. And then, once I endogenize them, they may be part of a repeated game, or they may be part of a more psychological game, and that I might really hate a product that I cannot return, but perhaps I change my way I think about it if I have a return option. So that's going to change the thresholds, and then we are back to the sort of the analysis at the end where what happens when you change those thresholds. But plus, we have to embed this on a bigger model of how those thresholds are determined. Yes, please?
This is a bit of like a more practical question. Is it useful to think about some filtering on the reviews that the system, the online system may apply, and then making it public knowledge, and then expect the system to perform better?
Right. Okay. So this is that was the last slide, which I skipped. So this last slide says, so imagine that I can actually filter. I observe from your previous purchases, so I get an estimate of your theta, and then I give the reviews broken down by people who have a theta like you and the people who don't have a theta like you. So that's what Amazon does here, rated by customers also interested in. So those are people like you, because you looked at this book, and they looked at this book, so they might have a similar theta. So I'm giving you a finer thing. So of course, if you do that, if you go back to the first book about climate science hawks, I don't want to know what the people who buy Trump's collected works thought about this book. But if you tell me about what other people who've bought serious climate science books thought about this book, that's going to be very relevant. So essentially here what we say is that if you do give this additional piece of information without hiding any information, the speed of learning increases. But conversely, if you create an echo chamber, the speed of learning may decline. And the echo chamber here would be, I only give you people who are like you, and I don't give the other group. That might actually slow it down. Why? Because I'm actually giving you less information, because I'm only giving you a subsequence rather than the full sequence. Yes, please?
I think it would be the role of the written comments with the results, because they kind of give the information about the initial.
Right, that's a great question. So in some sense, those comments are unique. So once they are unique, it's hard to think. But imagine that you sort of create a mapping from the comments to an additional signal. So imagine, like, for example, we started with dislike and like, but then I also read your comments, and that's like, I really love this product. I left a like comment, but I really love it, so perhaps that's like a third one. So that would be just like a refinement of the original one, so that will help. But that's, I think, is another good way of thinking about it. Yes, please?
There are some types of products out there for which, say you're buying a PC or something, and you might see a review where there's an overall score and then sub-scores that look at different categories of qualities. For example, one might have a rating for the memory or the speed or the sound, blah, blah, blah. How do you think that would impact the speed of learning?
I think that's a great question, and I don't know the answer, because essentially here's a different way of asking your question. Instead of a single dimensional good, imagine that the good itself is a bundle of characteristics, and each characteristic could be Q equals, Q1 could be high, Q2 could be low, etc. And then you could either get learning by characteristic by characteristics, or you could get learning for the average characteristic. And it's actually not clear which one would be better, because at the end of the day, you might think, well, more information should be good if I learn about the different characteristics. But if I care about the average of the characteristics, separating it by characteristics, I might be adding a lot of noise into the problem. So we haven't actually thought about that, but it's a good question.
So I have to jump in and say that there seems to be a lot of extensions and future work that can be done based on this work. We do have a reception on the
where some of that work can start.
Right, 6th floor in the Lids Lounge. So Daron will be there. So if you have more questions, you can have a one-on-one.